Integration, the second half of the calculus story. Okay. It is the opposite operation to differentiation, and we'll see why. We're going to show you how. You may remember when we started calculus, we started by wanting to solve a problem. And that problem was, how do we find the equation of a tangent when all we know is 1 point? And we needed to find the slope of the line, but we only knew 1 point. And that's where calculus came in handy. We're going to start integration in the same way by solving a problem. And the problem is, how do we find the area under a curve? It's all right if it's a regular shape. I mean, if it's a triangle, I've got a formula for that. If it's a square, I've got a formula for that. But something like this one here, under the curve y equals x cubed, I mean, we don't have a formula for that. So how on earth would we find the area underneath it? So to start off with, I guess the best I can do is estimate by using shapes that I do know. And I'm going to use rectangles here. Now, clearly, these two red rectangles that I've drawn in, the area of those two red rectangles will be more than the area under the curve. Okay. So what I do know is the area under the curve will be less than, theoretically it could be equal to, there is a chance, not a very big one looking at my picture, but there is a chance that it could be the same area. So 1 times 1 cubed and 1 times 2 cubed. All right, so I know it's going to be less than, maybe equal to, but probably less than 9. But I can also draw what we call inner rectangles. Those red ones we sometimes call outer rectangles because they're over the size of the area, so it's outer. And the inner rectangles are the ones we call which are less than the area. And so these two blue rectangles, and in fact the first rectangle really is just a straight line. It's a rectangle of height 0, you'll notice in this diagram. But clearly the area under the curve will be more than that amount. So I know then that I can trap the area under the curve in between, somewhere between 1 and 9. Now obviously there's a lot in between 1 and 9. I guess if I had to now estimate, the logical thing to do would be to average the two. So as an estimate, I'd say, oh, okay, I reckon, well, maybe it's around 5. It actually turns out the exact area is 4. So, well, it was better than 9. It's better than 1, but it's still not great. But what I can do to improve my estimate is increase the number of rectangles I use. So, same idea, but this time, instead of drawing 2 rectangles, I've drawn 5. The area is still over, but certainly by less than the last one. And so I now know it'll be less than. Now all of these rectangles have a width of 0.4, and then the heights, well, depending on where it is on the curve, so 0.4 cubed, 0.8 cubed, and so on. So less than 5.76. So we've certainly got that down quite dramatically from just 2. We went from 9 to 5.76. What about the inner rectangles? Let's have a look at those. They also have the width of 0.4, but the first one is, well, really a line. 0 cubed up to 1.6 cubed. That is 2.56. So again, we've trapped it into a smaller area. Oh, well, for want of a better word. The average of those ones, 4.16. So that's not bad. We've increased it to 5, and we've got a heck of a lot closer. Still not exact, though. So what I could do is increase the number of rectangles. So let's go crazy, and let's have 10 rectangles. Here we go, here are all the outer ones, all 10 of them. Now they've got a width of 0.2, and it'll be 0.2 cubed, 0.4 cubed, all the way up to 2 cubed. So I now know it's less than or equal to 4.84. And the inner ones, let's create those. And that turns out to be 3.24. The average of those two, 4.04. So we've got very close now. Still not exact. Well, what we can see though is if I was to keep going like that, I would get closer and closer to the exact value. So in fact, ideally, I would like that width to be how big? Yeah, I mean, if it could be 0, obviously it can't actually be 0. But if we use an idea of limits that we saw before, if we see what happens as that width approaches 0, we'll get an exact value. And that's the idea we're going to work with here. So all right, this is now just a random curve, y equals function x. Let's just have a look at one of those rectangles. Now, you might be looking at it saying, that's not a rectangle, look at the top of it. But remember, if we're going to approach towards 0, then the top of that curve would be as good as a straight line. So I can pretend that that is actually a rectangle. Area C, I will say, is the area. I'm going to come up with a formula. So capital A is now my function to find the area of the curve. Okay? So function C, or area C, will be the area from 0 to C. So under the curve from there to there. Area X will be the area from 0 to X. So the difference between the two will give me the area that I'm looking for. So the area we want is area X minus area C. Now that rectangle, remember I'm pretending the top is now straight because we're going to end up going towards 0. The width of that rectangle is X minus C. The height will be whatever function X is at that point when we substitute it into the function. So I now know that area X minus area C is approximately X minus C times function X. Okay, I'm just going to rearrange that slightly, because I know what function X is. So I'm going to make that the subject. If I make that the subject of this approximation, I'm going to say function X is approximately equal to my area X minus area C, this new function we're trying to discover, over X minus C. I'm going to write it slightly a different way. Instead of saying area X, I'm going to call it area C plus H, where H is the width of the rectangle. Okay? So it would be C plus H minus area C over H. It's starting to look a little bit familiar here, I hope. But as we said, we want to look at the limit. We want to get as small as possible. So if I make the H approaching 0, that width of the rectangle, then look at the formula. I now know that that function X will be exactly the limit as H approaches 0 of this new function I've called A, C plus H minus area C all over H. But remember, we said H is approaching 0, so C and X are approaching the same value. So I'm going to replace C with the X, because they're going to be the same thing as H approaches 0. Now look at this formula. Some function X plus H minus some function of X all over H. That is our first principles formula for differentiation. So in other words, the function curve, the equation of the curve, is actually the derivative of this area function that we're looking for. So we actually know the area function. All I have to do is work out, well, what would I have differentiated to get function X? And that's what we saw back in primitive function. Remember at the end of the last bit of calculus we did, we talked about the primitive function. So the equation of the curve is the derivative of the area function. All right, let's formalize this a bit. The symbol we use for integration is the long S symbol. You might know, those that have seen the symbol before might not realize that actually it is an S. And it is an S because it stands for sum. And what we're doing is adding up all those rectangles. Right? So that's where the integral symbol came from. It's from the letter S. In here we put the function that we know, and the dx is saying, hey, we're doing everything with respect to x. Like when we differentiated, we said differentiate y with respect to x. So that's why we put the dx there. Now A and B are where we're going from. So where does my rectangle start, or my area start? Where does it finish? So A to B. And it will be function B minus function A, where function x is that primitive function that we saw before. Remember, add 1 to the power over the power. And that's what we call integration. That's what we call integration. So let's now do the problem we estimated using rectangles, but now we're going to find that exact value. Remember, I said it was going to be equal to 4. Let's now prove it is indeed 4. So if I want to find the area under the curve y equals x cubed between 0 and 2, I know now that it's going to be exactly the integral of x cubed going from 0 to 2. Well, primitive function, when we're dealing with polynomials, add 1 to the power over the new power. So x cubed becomes a quarter x to the 4. And if you're ever unsure, differentiate your answer, and you should get back to what you originally had. So, okay, oh, geez, a bit unsure about that. Differentiate a quarter x to the power of 4. Well, I'd bring the power down. 4 times a quarter is 1. And I'd lower the power. Oh, x cubed, I do get it. So, terrific. It works. So, as I say, if you're ever unsure, go backwards, and you'll see whether or not it works or not. We then use square brackets, you notice, and our limits, again, we have them there. We're going from 0 to 2. And now we substitute in. And we substitute in the top one first. So 2 to the power of 4 minus 0 to the power of 4. And indeed, there's the answer we were looking for. 4 units squared is the exact area. Well, let's try another one. Difference with this question and what I just did. This now is not an area question. This is just simply a bit of mathematics. So you notice the last one, because it was to find an area, I put down units squared. This one here, we're just looking for a number. But the idea is exactly the same. Add 1 to the power over the power. So x cubed becomes a third x, sorry, x squared becomes a third x cubed. 1 becomes x, and then we're going from 2 to 3. Substitute in for 3 minus substitute in for 2, and the answer is just 22 over 3. Those of you who are observant will notice I've done one thing slightly different to when we did primitive function. What haven't I done? Yeah. Remember we said we could always have a constant, and I haven't bothered putting it in there? And the reason I haven't bothered putting it in there, imagine if I did. Let's go back to here, a quarter x to the 4. A quarter x to the 4 plus a constant. Then when I substituted in, what I would have got, okay, so imagine I'm substituting into a quarter x to the 4 plus a constant. And we're going from 2 to 0. That would equal a quarter 2 to the power of 4 plus a constant minus a quarter 0 to the power of 4 plus a constant. And because they're constants, I'm always going to get the situation of constant minus constant, which is 0. So when I'm substituting numbers in, I don't worry about the constant because I know they'll end up cancelling. So we don't normally write it in. All right, let's try this one. X to the negative 3. Be careful with this because we're playing with negative numbers. It's so easy when you add 1 to negative 3, get the answer negative 4 because 3 plus 1 is 4. But of course, we're dealing with negatives. Add 1 to the power, we get negative 2. Over the new power, so we've got minus a half out the front. You'll notice when I substituted in, I rewrote it as 1 over x squared is what I've substituted into. And I suppose that's because I'm dealing with fractions, and I probably wouldn't have used a calculator, whereas you people would have got an answer. So it's easier for me to calculate out when it's not an index form. So 9 over 800 is our exact value. 11A. Just one question. Oh, wow. How neat is that?